So we are supposed to start with pure substances. Pure substances एक बहुत basic सी चीज है. हर वो substance pure है जो सिर्फ single substance से बना हुआ है. As soon as we add something, it becomes an impurity. Water pure है तो ही हम उसे pure कह सकते हैं. Water में जैसे ही कुछ mix होगा तो वो pure water नहीं रहेगा. For example, muddy water, rain water, mineral water, sea water. These are the examples of impure substances. ये सारे वो examples हैं जिसमें water में कहीं ना कुछ mix हुआ होता है. और बात है कि हम प्योर वाटर को ड्रिंकिंग पर्पसेस के लिए यूज नहीं करते, मिनरल वाटर को यूज करते हैं, लेकिन केमिस्ट्री की प्योरिटी पॉइंट ऑफ व्यू से प्योर वाटर वही है जिसमें कोई और इम्प्योरिटी नहीं है. May that impurity be good for our body, like sodium chloride is most of the time, but हम उसे प्योरिटी पॉइंट ऑफ व्यू से इसी तरह हैंडल करते हैं. वैल्यूज मेल्टिंग या बॉइलिंग पॉइंट की प्योर सब्सटेंसेस की प्रिसाइज और प्रेडिक्टेबल होती हैं. ठीक है, हम इसे टेस्ट कर सकते हैं प्योरिटी ऑफ सैंपल के लिए. जहां कहीं भी आपके पास किसी भी स्पेसिफिक चीज को टेस्ट करना होगा, आइडेंटिफाई करना होगा, ठीक है, और आपके पास फिजिकल मेथड ही एग्जिस्ट करता होगा चॉइस में, यानी क्वेश्चन में उसने फिजिकली टेस्ट करने को कहा होगा, तो आप चीजों के लिए मेल्टिंग और बॉइलिंग पॉइंट्स यूज करेंगे. ठीक है, सॉलिड के लिए मेल्टिंग पॉइंट, लिक्विड के लिए बॉइलिंग पॉइंट. ये हम कॉमनली करते हैं फिजिकल टेस्टिंग में आइडेंटिफिकेशन पर्पसेस के लिए या कॉन्फर्मेशन पर्पसेस के लिए, इवन आफ्टर आइडेंटिफिकेशन. ठीक है, हमारे पास मेल्टिंग और बॉइलिंग पॉइंट्स हम इलेक्ट्रिकली हीटेड मेल्टिंग और बॉइलिंग पॉइंट अपैरेटस में चेक कर सकते हैं, व्हिच इज प्रीटी इजी. हमारे पास मैनुअल अपैरेटसेस भी एग्जिस्ट करते हैं, लेकिन हमारे पास इलेक्ट्रिकल अपैरेटसेस भी होते हैं which are far more accurate and can give us a value from up to 1 decimal to 3 decimal places. ठीक है, तो हम इन इलेक्ट्रिकल इक्विपमेंट्स को यूज करते हैं. दे आर प्रीटी इजी टू वर्क विद. ठीक, उसके अलावा इस पेज पर हमारे पास एक टेबल नजर आ रहा है आपको. ठीक है, देखने में तो ये टेबल बहुत सिंपल और इजी है, लेकिन एक्चुअली एग्जाम में इसे यूज किया जाता है एक डिफरेंट तरीके से. लेट्स गो थ्रू द टेबल. टेबल में हमारे पास सब्सटेंसेस हैं ऑन योर लेफ्ट. The physical state given is room temperature. Melting or boiling points quote किए हुए और physical states बताए हुए हैं. It can be either gas, liquid or solid. But how this question is manipulated in exams is very important. First, let me tell you कि जरूरी नहीं है कि वो आपके साथ ये room temperature पर ही working करवाएं. वो किसी भी टेम्परेचर पर फिजिकल स्टेट चीज की पूछ सकते हैं. ठीक है, वो 20 डिग्री सेंटीग्रेड भी हो सकता है, वो 100 डिग्री सेंटीग्रेड भी हो सकता है, और वो कोई और टेम्परेचर इससे कम या ज्यादा भी हो सकता है. इट कैन बी नेगेटिव, इट कैन बी पॉजिटिव. लेट्स कंसीडर दिस टेम्परेचर जिसकी हम बात कर रहे हैं एज गिवन टेम्परेचर. रिमेंबर, दिस टेम्परेचर वैल्यू वुड ऑलवेज बी कोटेड एज अ पार्ट ऑफ द पेपर. The two more pieces of information that you will require as a part of the question would be the melting point of the substance and the boiling point of the substance, and both are usually stated in degree centigrade as well, right? So हमारे पास ये सारे के सारे डिग्री सेंटीग्रेड में दिए हुए. फॉर एग्जांपल, हम किसी सब्सटेंस की बात करते हैं, x है, और गिवन टेम्परेचर हम कंसीडर कर लेते हैं 100 डिग्री सेंटीग्रेड है. द मेल्टिंग पॉइंट टोल्ड टू अस इज 115 and the boiling point given to us is 444. What would be the state at 100 degrees centigrade? Physical state.
Physical state. Sir, could you repeat the question one more time?
The temperature is 100 degrees centigrade. What would be the physical state of substance X at 100 degrees centigrade when its melting point is 115 degrees centigrade and its boiling point is 444 degrees centigrade? What would be the physical state? Would it be a liquid, a solid, or a gas?
Gas, I think.
Sorry, what did you say?
So would it be gas, the state?
No, that would be a solid. Now, let me tell you something which is not given here as a part of the book. If the given temperature, whatever that temperature, right, is less than both melting point and boiling point, that substance is supposed to be a solid. Okay. And pretty easy, and the exact opposite, if the given temperature is actually greater than both the melting point and the boiling point, the substance is a gas. only when the given temperature is in between the melting and the boiling point, when the given temperature is actually greater than the melting point. In fact, we shouldn't be using the greater than or equal to sign. Only the greater than sign would be a better explanation for it. And is smaller than the boiling point, then the substance is liquid. So this is the formula you need.
Sir, there would be questions like these in the exam?
There have been questions in past. The past papers have a lot of questions in like this in exams. And let me tell you, these questions have been a part of paper 2, 4, and 6, all three of them. Paper 6 recently, but mostly paper 2 and 4. So this simple formula can give you a very good idea how would we able to do it. Take a look. This formula has actually already been applied to this table. If the temperature, remember the temperature is 20 degrees centigrade in this table, right? So 20 degrees centigrade is actually smaller than 115 and 444. So the given substance is a solid. The 20 degrees centigrade is greater than 0, which is the melting point, but smaller than 100, which is the boiling point. It lies somewhere in between. So that's why it's a liquid. And this 20 degrees centigrade is actually bigger than both 210 degrees centigrade and minus 190 degrees centigrade. Both values are negative, so it's a gas. So this formula has actually already been applied to this table. Okay. There are many points in this book where the teacher needs to tell you something extra so that you are able to solve your questions, and especially the kind of questions that have been a part of past papers.
This is kind of confusing because these formulas aren't given in the exam, in the books or so.
Yeah,
if it's not given, then how are they asking a question?
Yeah, that's where the role of the teacher kicks in. I am supposed to tell you that. If I'm not doing that, I'm not doing justice with the stuff I'm teaching you, right?
Okay, sir,
now, teachers do it in different ways. Some teachers teach it during the teaching period, and some teachers actually discuss this kind of stuff when they are practicing the past papers with you. Now, both options are good. It's just different strategies. You can pick any of those strategies. But if you don't tell your students this kind of stuff, even when you're practicing the past papers with them, and the papers are just like 3 to 4 months away, then you're not doing it justice.
Yes, sir. Should I write this down in my book?
Yeah, go ahead. I usually ask my students to write most of the stuff that is not given in the book and can be a helping material, to write it then and there on the book, on the same page. So whenever you're going to revise right before the final papers, it's pretty easy for you because all the material would be right there in the book.
Yes, sir. Exactly. Okay. All right. Down.
This is a greater than sign. I hope my writing is understandable.
Yes, sir. It's understandable.
So for pure water, the melting of boiling point can be the exact values what we teach and what students are supposed to memorize. You're supposed to memorize these two values. All right. You're not supposed to memorize the melting and boiling point of any other thing in chemistry's book, apart from a couple of values which would come ahead, but the melting and boiling point of water. Now, as I said, the presence of impurity lowers the melting point. That's the way to write it, or raises the boiling point. So that's the way to write it, right? If that is clear, we can move on.
Yes, sir, it's clear.
Good. Now, moving on to heating and cooling curves. Whenever we change the state of a substance, we can always draw a curve on the graph. That we can do by simply measuring the time or the progress of our entire process against the temperature values. For example, we can start off by taking a solid. We can heat it up in an oil or a water bath. In a manual system, we can convert it first into liquid, then we can keep heating, and then we can convert it into a gas. And we can keep plotting the values over a graph paper, although this is not the same graph as the diagrams, but we can keep noting down the time, we can keep noting down the values, and we can properly plot a graph. That graph, in case if we were heating, would known as a heating curve. Unfortunately, the heating curve is not present in this page. So I'm going to move a few pages ahead on this book where you have the heating curve so that I can show you the heating curve. Just a second, it's actually a few pages ahead. This one, there you go. There you have the heating curve. So we can plot it in time on x-axis and temperature on y-axis. We'll start off with a solid, then there would come a time when it would start melting into a liquid. Then if we keep heating it up, slowly the liquid phase will face a time when it would start boiling and be converted into gaseous phase. So that's how a heating curve goes. So if we keep on noting down the time and the temperature values, we can literally plot a curve known as heating curve. This is a heating curve. A heating curve can be easily explained by a few steps. We start off with a solid, and then comes a straight line, a line that is exactly parallel to x-axis and can always be extrapolated to find out the temperature, which we can call the melting point of the substance, whatever we are heating. And then there would be some liquid state, and then again there would be a line parallel to the x-axis. Just like the previous one, we can always extrapolate that line back onto y-axis and can find the boiling point of the substance. Right?
Okay, yes, sir.
There are a few more things that you should know to handle for a heating curve. Let's put them up. Give me a second. Now, take a look. As soon as for the straight line starts, let's say it starts over here. So you can always start noting the time when it started melting, and all of the substance will probably melt at this point. So that's the point. So this is the time taken for the melting process to be completed. As during the melting process, the temperature stays constant. The energy we put in the amount of heat is used to overcome the forces that are holding the lattice or the structure together.
So it's like constant when it's like it's continuously increasing. It's not like it's one value, right?
Yeah. It's just a single value. That's why the melting point is a single value on the temperature scale. Let's say we were working with water, although the substance is not mentioned over here. So this must be the 0 degree centigrade line.
Okay, understood.
Okay. During this melting process, remember, the temperature will not change and will stay constant.
Okay.
That's actually a hint for you to get that it's melting point. And this one would be the time taken for the melting process to complete. You can note the time by noting the initial and the final values for this straight line. And if you do the same for this straight line, you would be able to calculate the time values for the boiling process to get completed. And this, of course, is extrapolated towards the y-axis would give you the boiling point value. Let's say we were talking about pure water. This is bound to be 100 degrees centigrade.
Okay.
All right. Remember, if the temperature along with the time keeps on increasing, it happens when in its specific state, either solid or liquid or gas. At this point, remember, there are actually two states that are coexisting, solid plus liquid. Because the solid is being converted into liquid, so both the states coexist at this specific line. Just like that, this specific line, both the states of liquid and gas would coexist. Because during boiling,
it depends on the sufficient energy given. If the sufficient energy is given, then we move to the right and we're converted into gas. If the sufficient energy is not given, it would stay as liquid.
That is correct, right? So in case of boiling, once again, the energy that we put in makes the particle move faster, overcome the attractive forces that holds a liquid together, and slowly the molecules move far away from one another, and hence they are converted into gaseous phase. Right? So for any heating curve that you have, and there has been some past paper questions, you can always extrapolate this line to find out the melting point. I hope you can do that on a graph. You can extrapolate this straight line to find out the boiling point. I think that's easy too. You already know which states exist at which specific part of the graph. This has been a part of past paper questions, but now they consider it too easy and they are not thinking about giving these questions from the previous 4 to 5 years. However, you would find many questions like these back in 2010 to 2014 papers, all right? And
So how many marks do they have? Do they contain?
usually
Cooling curve. 2 to 4. Okay.
there are different questions about this graph and usually 2 to 4 marks, right? And I am coming to the rest of the marks because this paragraph is also important when we're going to consider those marks. You can always calculate the time taken for the melting process or the boiling process. I've already told you how to calculate that, right? So now you know how you can plot a heating curve if that comes as a part of practical. However, if that comes as a part of extended theory question and you have the graph in front of yourself, you can always work it out. Remember, reversing this experiment will give you a cooling curve. The temperature stays constant during condensation and freezing. Condensation is the exact opposite to melting, and freezing is the exact opposite to boiling. Sorry, my bad, I said the opposite. Melting is the exact opposite to freezing, and boiling and condensation are exact opposites. And the energy is given out. Remember, condensation and freezing are exothermic processes, the processes in which energy is given out. Melting, evaporation, and boiling are endothermic processes. They require energy for the process to move ahead.
Yes, sir. Understood.
Okay, good. Then if you understand that the reversing of the experiment is going to give us a cooling curve, so let's go back to the page we were at and talk about that curve, because that curve, cooling curve, is actually present on the same page we started off with. Let's see, there you go. At the bottom of page 26, we have a cooling curve. Now the cooling curve is drawn in an opposite manner to the heating curve. You would see that it starts off from the top and not as solid state. In fact, it starts as gaseous phase. And there comes a point where we liquefy the gas to convert it into a liquid. And then there is another straight line where the liquid freezes to be converted into a solid. And as you can see, the numbers are extrapolated to find out the liquefaction temperature or the freezing temperature. All right? Remember, in these processes, as they are opposite, two of these processes will take in the energy while two of them will give the energy out. Any processes regarding cooling curves give out the heat energy, and any processes regarding the heating curve take in the heat energy. Now, there are differences between the curves of a regular pure substance and impure substance. Naphthalene is actually a pure substance here, and because it's a pure substance, its melting or boiling points are pretty sharp. You can always extrapolate this value and get an exact answer because this is a straight line. However, wax is actually an impure substance because it's a collection of many organic molecules. It's actually a collection of hundreds of organic molecules, hence an impure substance. And you would see a straight line over here, which you can extrapolate to get a melting point or a boiling point value. So what we say is that they melt or boil over a range of temperatures. For instance, if you perform the experiment for the melting point of wax first time, you might get the temperature as 70 degrees centigrade. The second time it might be 72. It means wax is an impure substance. That was bound to happen. Specific and set temperatures, accurate ones, only come out for pure substances. However, impure substances don't do that. Are we good?
Yes, sir.
One more thing, when a solid is melted or liquid is boiled or vice versa, in case of a cooling curve, the temperature stays constant. This produces a straight line parallel to the x-axis until this process is complete. The same is true in reverse when a gas condenses or a liquid freezes. Make sense?
Yes, sir. It makes sense.
Okay. There is, however, one small point in terms of practical paper that I don't want to miss, and that's given right at the bottom of this diagram. Remember, in any kind of heating apparatuses, be it a melting point apparatus or a boiling point apparatus or a manual one at that, a water bath can be used for melting points below 100 degrees centigrade and an oil bath for those above 100 degrees centigrade. This is a water bath. If the beaker was filled with oil, it would have been an oil bath. I hope you understand this point. Underline this one up so that whenever you're revising, you can revise this specific point. This is important in terms of paper 6. Let me tell you, it have been a part of difficult variants, not the easier ones, 1 and 3. It has never been a part of variant 2.
Okay, so variant 1 and 3, and
Right.
but not variant 2. Okay.
Right. And this means that at one point, we can even expect a difficult question in variant 2 as well.
Okay, so.
All right. So this is what heating and cooling curves are all about. The 3 to 4 marks are about the energy questions, whether the energy is being given out or taken in, or how to extrapolate the graph questions and find out the values of melting, boiling, or freezing points, how to work with impure or pure substances graphs as they are different. Remember, whenever we talk about pure substance graph in this straight line, the words that we use is that they give a sharp melting point. Sharp melting point or a sharp boiling point term is used for straight lines. If we don't get straight lines, we say they are not sharp. Sharp means accurate. However, this word has pertained for a long time for this kind of phrases. We still use the word sharp for melting and boiling points.
Okay.
All right, let's move on. Next up is types of mixtures. Mixture is made from 2 parts. Mixture is exactly the opposite of pure substances. As soon as we make a mixture, we actually turn both the substances impure. Now, mixtures can be made out of solids, liquids, and gases, and there are a number of ways how these 3 states can be combined. Usually, we use solutions in terms of mixtures. Solution, I believe you understand already, is a part of 2 ingredients, that is solute and solvent, right? So solute is often called the solid that we use to dissolve in liquid, and the liquid which actually dissolves the solid is known as a solvent. This is the most easiest way how we define solute and solvent, but that's not the exact definition. As soon as we are done with topic 2.2, we'll come up with the exact definition. However, there is also one kind of mixture which is known as suspension. Suspension is actually the sustaining of fine particles in a liquid, so much so that they don't even settle down at the bottom because they're heavy, and they don't float on the top because they're not light enough. Okay, I think this needs to be explained with the help of a diagram. Okay, let's suppose this is a liquid, and in this case, our solvent. If we throw something heavy into it, of course, you understand that heavy thing would go right at the bottom and settle at the bottom. We say it's usually insoluble. If something dissolves in it, it is broken down and disappears in it, like salts do. There are some things which do not dissolve and float on the top of the surface, like wood does on the top of water. However, suspension is something different. Suspension means something that can be divided into very small particles. It does not flow on the top because it's not light enough. It does not settle on the bottom because it's not heavy enough. Instead, it suspends right in between, hence the name suspension. Suspensions are commonly used for medicine, and common suspensions that we do take are when we facing problems like fever or common cold or cough, and the medicines for most of these things are suspensions, usually not for adults but children.
So what
And
about
as
oil? If you mix oil with water, it's not at the bottom.
they are completely insoluble. For most of the oils, they actually tend to float on the top of water. Most of the oils. Actually, this list includes cooking oils. For cooking oils, you might have noticed that the water every time stays at the bottom and the oil sticks on top. It actually floats on top of the water. You may tend to mix it with one another. As soon as you do, and as soon as you stir them up, they might seem mixed. But if you give them some time to settle, the water being heavier in density will go to the bottom, and the oil being lighter in density will stay on top. This is actually the example of two liquids which are not soluble in one another, and the one with the heavier density settles down at the bottom, and the one with the lighter density actually makes a layer up top.
Sir, do you have any example of suspension, like any like mixture that creates suspension?
Yeah, of course. You can go ahead and take a glass or a beaker of water. You can fill it up with the common clay or sand we usually find in homes. If you are going to filter it up, you will be able to take out all the sand that has dissolved at the bottom. But you'll find out the water is still not pure and has a slight tint of sand-based color. It would have the soil-based appearance. The water is still brown. The water is brown because of the suspension. There were some particles which were actually heavy. As soon as we throw sand into water, the bigger particles which are heavy settle down at the bottom. But there are some sand particles which are pretty small and light. They actually try to stay as suspension, because of which the color of water seems to be brown. You can easily do that experiment at home. Okay. And even after filtering, if you filter this water, you will be able to take these one out, but you won't be able to turn the color of water colorless. It would still be light brown, as if it still had some mud particles. And no matter how many times you filter, you won't be able to take them out, because they're small enough to pass the filter paper. However, they're still not heavy enough to settle down at the bottom. Sometimes the suspension, if given the appropriate amount of time, settle down at bottom. In this case, the suspension systems, if we are using that, because sometimes we use suspensions as medicine or juices, there is a common statement you'll find written on top of them. As soon as you read this statement, you will automatically can easily consider your system as suspension. Shake well before use. That's often written on top of juices, on top of medicine bottles, and stuff like that. As soon as you see that statement written on top of something, you can automatically get an idea that it's a suspension. You need to shake it well before you use, so that the particles which probably have settled down at the bottom will again suspend right in the center. Right?
Okay, understood.
There are a couple of definitions for solutions over here, but I'm going to intentionally keep these definitions, and I'm going to do them with this part. I'm going to combine some parts of the book to make the stuff easier for you to understand. Okay, this part. I'm going to cover this part up right before I start 2.2. All right? So we were talking about solution. The proper way to define solute is the solid that dissolves. The proper way to define a solvent, the liquid in which it dissolves. You may change the words of solids and liquids, and you can change them with whichever physical state of matter you're using. Right? Okay. Now, there are different kinds of solutions and on different bases. Let's consider those solutions one by one. The first basis is solubility. On the basis of solubility, we actually have two types which are given right over here. If the substance dissolves in the solvent, it is said to be soluble. If it does not dissolve, it is known as insoluble. I think that's pretty easy to understand, right?
Yes, sir.
But let me tell you, the substance has to be solid for these words to be used. If you're mixing a liquid into a liquid, then we use a different terminology. Then the terminology
miscible would be, I think.
Right, miscible. Then we use the term miscible and immiscible, and they work in the similar way as soluble and insoluble. The only difference is that we use soluble and insoluble for solid solute and liquid solvent. We use the word terms miscible and immiscible for liquid solute and liquid solvent. Are we good?
Yes, sir. Sure.
Okay. So keep the terminology in mind so that you can use the exact one whenever it comes as a part of the paper. Now, next up is in terms of concentration. There are two kinds of solutions when it comes to concentration. A solution that contains a high proportion of solute is known as concentrated solution, and the opposite one containing a small proportion is known as a dilute one. Okay, so remember,
if there's more solvent, it means it's concentrated. If there's more solute, it's dilute.
right. And remember, they're relative terms. For a system which you can define as concentrated, there has to be some other system in comparison. If you're facing a single solution, you can't call it dilute or concentrated. You can always call solutions dilute and concentrated in relative terms. Let me explain. If you have a glass of water at home and you filled it up to the mark, and you took another same glass and filled it up with the same mark, and you're going to dissolve a tablespoon of sugar, 1 tablespoon into the first glass. However, you're going to add 2 tablespoons to the second glass, right? Then this one is supposed to be the concentrated and this one is supposed to be the dilute solution. Why? This one has a higher proportion as compared to solution 1.
It depends on comparison.
Right. Relative means comparative.
Depends on comparisons, right?
Right.
Yes.
Concentrated and dilute solutions come out of comparison. We always require a comparison in order to state concentrated or dilute solutions. Now, the last type.
We have only one substance. When we only have one substance, it's not considered as anything until we have another substance that we can compare it to.
Right.
Then we can consider what is concentrated, okay.
Right. That is correct. But sometimes, in order to simplify
both of them
our work,
are like,
in order to simplify our work, or in order to simplify the question in exams, they might simply straight up use the word concentrated or dilute to give you an idea without considering the comparison. Right?
okay.
Like we do with people. We call someone bad or good without even comparing them with any other person. We call someone white or black without even comparing them with any particular person. How do we do that? We understand the standards and we go with the common of standards to talk about that. However, your papers can do the same. They can simply give you the question without giving you the comparison and tell you whether it's concentrated or dilute. That way, it is to ease the question up. They can't always keep the comparison for you there, which will definitely elongate the question and will take more time for you to read it and comprehend it. Right? So for the sake of ease, sometimes we do not consider the comparison.
Okay, all right, okay.
Okay, which brings us to the last type of solutions. So I am dividing solutions into different categories and then different types. In solubility, I explained soluble and insoluble, or miscible and immiscible, concentrated or dilute. Then there is another type which is written over here, that is saturated solution. Now I'm going to define 3 types over here, which are actually spread all over the book, but I'm going to explain right on this page so that we don't have to go to different pages on the book. And this one. The third one has been a part of your course.
Saturated would be the substances that contain only hydrogen and carbon.
No, that's the saturated hydrocarbon, and that's a part of organic chemistry.
Yes.
We're talking about saturated solution as a part of general or applied chemistry, which applies to both organic and inorganic substances. Right? So saturated solution has the solution, is the solution actually, which already has the solid which it can dissolve. For example, we try adding a solid to a liquid. There would come a point when no more of that solid would dissolve at that specific temperature. It would known to be a saturated solution. Saturated means it is already up to its saturation point. It has already dissolved that much amount of solid which it was capable of.
So, sir, what's
an example
the
over here?
definition, sir, if the definition is asked?
Yeah, this is a similar one. Or you can take the exact definition from glossary as well, which is pretty similar to the words. They've just changed the start over there. Okay, so let me give you an example. The common household glass that we talk about usually contains 200 50 ml or cubic centimeter of water. Fill that glass up. Try taking the common tablespoon that we usually eat with of sugar. You can dissolve the first one into it. It would easily dissolve. The second one, that would dissolve with some stirring. The third one, a lot of stirring would be required, but would be dissolved. As soon as you go into the fourth one, you would see that the solid would settle at the bottom, and no matter how much time you stir it, it won't dissolve. If the solid stops dissolving at a specific temperature in a certain amount of solvent, the solution is known to be a saturated solution. Any amount less than that, let's suppose we have only dissolved 2 tablespoons so far, would be known as unsaturated solution, because you can still saturate it by dissolving more. So half a tablespoon, 1 tablespoon, 1.5, 2 or 2.5 are all examples of unsaturated solutions, because you can always add more.
Same thing with reactions, sir. Like if I continuously react something with a substance, there would be a point where it would stop reacting. So that would be considered as a saturated liquid solution too.
If you're mixing, yeah, it would. If you're talking about a chemical reaction, we usually don't use the word of saturation with chemical reactions where they stop. We have different terms for that, which we usually explain in chapter 7. So
solutions, things that can be reversed, okay, like the reactions, solutions.
The solutions that form after a reaction, or the solutions that we simply form after mixing? Which one are you talking about?
That's why I was just confused on reacting. Okay, so solutions are when we mix something.
Right, solutions the one with we mix something. It's not about a chemical reaction, it's simple physical mixing. Right?
Understood.
Okay, so saturated, when there is enough solid which it can dissolve at a certain temperature. Unsaturated, less amount of solid which it is capable of dissolving. However, supersaturated is something in which
sorry, your voice is lagging, sir.
Just a second.
Sorry, your voice is lagging, sir.
Just a second. All right, so I was trying to explain supersaturated solution. Supersaturated solution has more amount than saturated solution. How are we capable of dissolving more amount than we already can in a solution? That we can do by simply increasing the temperature. Let me amaze you by telling you that if we increase the temperature of water in this glass and we take it as high as up to its boiling point near 100 degrees centigrade, you won't just be able to dissolve these 3 tablespoons. Instead, you would be able to dissolve 4th, 5th, 6th, and probably 7th tablespoon as well.
So how is that possible?
Increasing the temperature, you can allow us to dissolve more solid into a certain liquid, but that doesn't happen to every solid and every liquid. Here comes the definition of solubility then. The concentration of solute in a saturated solution of the solute for a specific solvent at a specific temperature is solubility. The solubility for different substances is different. Some increase with the increase in temperature, some don't. For example, the most of the warm desserts that we make, we are actually able to add more sugar to the system by simply warming the water up.
That's true, yes.
There are some desserts which contain a lot more sweetness than the others, and most of the desserts that contain a huge amount of sweetness is actually because they're served warm.
Yes,
that's because at that specific temperature or higher temperature, it would be capable of dissolving more solid. In that specific case, sugar.
That's why mostly all the desserts are heated and then cooled. So
right. That is true.
Because of
So remember, the solubility of most solids increase with temperature. However, sometimes when a saturated solution is cooled, it can hold less solute at the lower temperature, and some of the solute crystallizes out. There are common desserts in Pakistan and all over the world which are usually made during warm circumstances, And as soon as they're cooled up, some of the sugar comes out in the form of crystals, and we can find it right on top of that dessert. Right? This is going to happen to most of the solids which we can dissolve a higher amount of at a higher temperature. Okay. If you can remember these different types of solutions,
I'm still kind of confused with this last part, this last paragraph, like how it creates crystals.
It's pretty easy. It's pretty easy. Let's say we take a glass of water, we heat it up around near to its boiling point, and then we are capable of dissolving all several tablespoons as I showed over here. Now, take this glass away from heat, put it at room temperature, wait for a couple of hours for this temperature to be cooled down to room temperature. You would see that the temperature of this water will come down to room temperature. When it does, you would see that these fourth, fifth, sixth, and seventh tablespoon would be lying at the bottom of the system in form of powder. It means that the solute crystallizes out as soon as the temperature is lowered down. So the solute only stays in if the temperature is higher. If the temperature is lowered again, the solute comes out again. So it works in a loop, right? Sometimes it has been a part of previous course, but it was taken out. The numerical questions about this specific task has been taken out in 2016 syllabus. So we don't teach it anymore. Otherwise, if you're going to look at past papers previous or before than 2016, you'd find simple questions that, for example, at 100 degrees centigrade, we dissolve 90 grams of a specific salt in water. And at 20 degrees centigrade, we were only able to dissolve 27 grams of that salt. For example, the solvent was taken to 100 degrees centigrade, 90 grams were dissolved. When it is taken back to 20 degrees centigrade, how much of the salt will crystallize out? And the answer is as simple as a subtraction question, right?
Yes, sir.
Okay, 53. Okay.
Okay, understood.
All right. So, however, these questions are not a part of course anymore. After 2016, they were taken out of the syllabus. Okay, so let's clear it up and let's go back to the point. All right, we are almost done with time.
Yes.
I'm not gonna do anything anymore now, but for tomorrow, we're going to start with 2.2, separating and purifying substances. And as this is discussed with different types of mixtures, sometimes concentrated or dilute or miscible or immiscible, that's why I wanted to go through all those words first. Now you know how many different kinds of solutions we have, and whenever we're going to discuss them in terms of separation, you would understand what I'm talking about, right? Any questions?